Okay, we are going to carry on with this example. We are going to carry on with this example that we've done. So we have found our second moment of area. Okay, so what I'm going to call now is I'm going to call where this point over here, I'm going to call this our point A, right? And over here, this is or exactly at us over here. This is our point C. Okay, so let's determine the first moment of area for point A. Okay, let's determine first moment of area for point A. Okay, so QZ at point A is equal. So I'm going to divide this in such a way that this will be our, what I'll do is I'll copy and paste this diagram again. Okay. Zoom out. Okay, so this is where we want to find at point A. Yeah, this is at point A. And we are going to divide this. I'll call this our flange. And then these two regions are our web. Okay. Then from here, so we're going to do the QZ of flange plus by the QZ of the web. Right. So you see the flange and the web. So we'll have the width for the flange is 50. The depth is 10. And then the centroid, we know that over here, this is our centroid. Let me, right? So we know that this is the centroid, right? So the centroid is 20 plus 30 plus 10 is 60 minus by 10 divided by 2. Okay, so that is for the flange. Okay, so let me check again. Width is 50, depth is 10, centroid is 60. So 20 plus 30 plus 10 is 60, then 10 divided by 2. Then plus by you have two webs, so you need to put a 2 in front, right? You need to put a 2 in front. The width is 10. The depth is what? The depth is 30. Okay. And then the y bar is 20 plus by 30 divided by 2. Okay. So this will be equal to 60 minus 5. No, 60 minus 5 times 10 times 50 is 27.5 times 10 to the power 3 plus by 20 plus by 15 times by 30 times 10 times 2, which is 21 times 10 to the power 3. So this is equal to 27.5 power 3 plus by 21 power 3. 27.5 power 3 plus by 21 power 3 is equal to 48.5 times 10 to the power 3. Millimeter cube, or 48.5 times by 10 to the power minus 6 meter cube. Okay. So from here, we can calculate our stress at point A. Okay. So this will be good. So V we don't know. IZZ we know is 4.86 times 10 to the power minus 6. Our QZ is 48.5 times 10 to the power minus 6. And then our thickness is twice because you have left and right, and then the thickness is 0.01 meters. Right? So this will be equal to 48.5 power minus 6 divided by 4.86 power minus 6 divided by 2 divided by 0.01 is equal to 498.971. Vy. Okay. We still cannot determine what Vy is yet for now because we now have to calculate at the centroid. Okay. So now we are going to determine, okay, we're going to determine Q at point C. Okay. So point C will be somewhere, is exactly at the centroid. Okay. So from here, you find QZ at point C. You just need to do QZ at point A plus, okay, plus by this area now, because we have not considered the first time. So the width is still 50. The depth is 20. The Y bar is 20 divided by 2. Right? So this will be equal to 48.5 times 10 to the power 3 plus by 10 times 20 times 50 is equal to 10 times 10 to the power 3. So this will be equal to 48.5 power 3 plus 10 power 3 is equal to 58.5 times 10 to the power 3. As we expected, it has the largest first moment of area, okay, millimeter cube, or 58.5 times 10 to the power minus 6 meter cube. Okay. Then from here, we are going to write out our, we're going to find the shear stress at point C. Sorry. So shear stress at point C is equal still the same Vy over 4.86 times 10 to the power minus 6. Okay, and then you have 58.5 times 10 to the power minus 6. Now the thickness is different. The thickness now is 50 millimeters, so 0.05. So hold on. So this will be equal to 0.05. So this will be equal to 58.5 power minus 6 divided by 4.86 power minus 6 divided by 0.05 is equal to 240.70. 0.74, sorry. Right? So which one should you use now? Are you going to use the shear stress at point A? Or are you going to use the shear stress at point C? So Vy is a constant. Note, okay, so note that Vy is a constant. Right? Regardless of whether point A or point C, Vy is always going to be the what? Going to be the same. Right? So for this case, we realize that shear stress at point A is greater than shear stress at point C because Vy is constant. Okay, so therefore, the shear stress at point A is tau max. Right? That's the maximum. Okay. Why that is a maximum? Because it is the biggest. If you look at A, it is the biggest first moment of area you can consider with the smallest thickness. Whereas at point C, you have to consider this, the area goes bigger, but the thickness also what? Increases. So that will not work at all. So therefore, okay, so therefore, 498, or so the maximum shear that we see 60 times 10 to the power 6 is equal to our tau max is 498.971 Vy. Okay, so therefore Vy will be equal to 60 power 6 divided by 498.971 is equal to 120.247 times 10 to the power 3 Newton. So this is the largest force that you can use. Okay, any force higher than that, the structure will fail. Okay, so some student did ask me, what if you use the shear stress at point C? Let's say you did not know this, you calculate based on shear stress. So if you base on shear stress at point C, right? Let's say you're going to use that shear stress at point C. So what you will get is you will get 60 times 10 to the power 6, and then this will be equal to 240.74 Vy. So you have calculated Vy is equal to 60 power 6 divided by 240.74. It becomes 249, right? It becomes 249.232 times 10 to the power 3 Newton. So when this is the case, this no doubt your forces are higher. If you apply the forces at this magnitude, okay, the shear stress at point A will exceed, right? Will exceed 60 times 10 to the power 6 Pascal. This will result in failure or in overloading, result in overloading of the structure. Okay, which will not work at all. Are we clear? Okay, so it's important. So as I said, the most important thing I want to show you about this question, right, is not necessary. If the thickness is not constant, okay, the shear stress is not necessary at the centroid, like for this case. Any questions from anyone so far? No? Okay. So the next one, I'm going to look into a different. So the term test, we will stop here. Okay. Test up to here. Okay. Test up to here. Okay. I don't think it's fair. This is I cannot finish like half an hour to teach you the next section, but I'm going to introduce you to the next section. Okay. Right. So the next one we're going to look at, the next topic we will look at is going to be shearing stress in thin wall section. Okay, we're going to look at shearing stress in thin wall section. Okay, so shearing stress, so this is a so-called new subtopic. Okay, so shearing stresses